Welcome to The Explainer. Listen, if you're a developer, you have absolutely felt the shared collective pain of inheriting a messy, completely unpredictable legacy system. We have all been there, right? Staring at a code base where every single endpoint feels like it was designed by a different person on a completely different day, and none of them are talking to each other. Well, today we are going to fix that. We're looking at the global principles and best practices of RESTful API design.
So, let's just jump right in and ask a pretty tough question. Is your API truly RESTful? Because I've got a secret for you. Simply returning JSON from an endpoint like /deleteUser.id equals 123 is a far cry from true REST architecture. Honestly, just because it's speaking HTTP and formatting as JSON does not mean it actually has the structure, predictability, and scalability of a genuinely RESTful system.
Man, I absolutely love this quote from Streppy. Most APIs claiming to be RESTful are actually a collection of HTTP endpoints held together by hope and extensive documentation. It's great developer humor, sure, but it hits hard because it is just so incredibly true. When you lack architectural principles, your API essentially decays into an inconsistent mess. Applying true RESTful principles is literally the ultimate cure for all that API chaos.
All right, Section 1, Anatomy of RESTful APIs. Let's talk about building that foundation.
So, the architectural foundation of REST was originally laid out by Roy Fielding way back in his 2000 dissertation. He established these 6 guiding principles. Now, if a service interface is actually going to be referred to as RESTful, these constraints absolutely must be satisfied. We've got a uniform interface, client-server separation, statelessness, cacheability, a layered system, and code on demand. Together, these 6 core constraints transform what would be a basic, brittle web service into a highly predictable, decoupled, and super scalable RESTful system.
Let's really zero in on one of the most critical ones here, statelessness. The crucial point you need to take away is that statelessness isn't just a best practice rule. It is the absolute bedrock of a scalable system. Every single request must contain everything the server needs to fulfill it, period. There is no hidden session context living on the back end. And why does this matter? Well, because it allows your API to horizontally scale behind load balancers. Literally any server node can handle any request without dropping user sessions. It is a real game changer.
Moving on to Section 2, Designing Predictable Resource URIs, nouns, not verbs.
Okay, when we are framing out our API skyscraper, we have to design predictable paths. Now, on the left, we've got action-based URIs. Things like create order or get users. This is bad practice. Actually, it's terrible practice. Instead, we need to model our resources as plural nouns, just like you see on the right, with orders and users. We let the HTTP methods handle the verbal action. When your URIs are predictable like this, client developers don't have to constantly guess what your endpoints are called.
But hey, we can't just stop at naming them well. We have to structure them well, too. You really want to keep your hierarchies shallow. Think collection, item, collection. You want to avoid mirroring complex internal database structures or those deeply nested joins. A path like /users/1/orders/99/products, oof, that becomes incredibly fragile and just a nightmare to maintain. Keep your URIs flexible. Keep them simple.
Okay, Section 3, HTTP methods and idempotency. This is all about the uniform interface.
To interact with our beautifully designed nouns we just talked about, there are specific HTTP verbs you should strictly use to completely eliminate guesswork. Get reads data, post creates it, put replaces a resource entirely, while patch just does a partial update, and delete, well, of course, it deletes. Sticking strictly to these semantics means your API aligns with standard tooling, proxies, and caching layers right out of the box. But I want you to notice that third column, idempotent.
So what exactly is idempotency? It's an operation that yields the identical result regardless of how many times it is executed. Think of it kind of like a crosswalk button, right? Pressing it 10 times doesn't make the light change any faster, and it definitely doesn't trigger 10 lights. If a network timeout happens and a client retries a put or delete request, it won't create duplicate records or cause weird unintended side effects. A duplicate post, however, might accidentally create 2 identical orders. Understanding and implementing this idempotency is absolutely vital for network reliability.
All right, Section 4, Strategies for API Scaling, Handling High Traffic Gracefully.
Look, once you build a great API, people are actually going to use it, so you need to handle that traffic gracefully.
First up, pagination and query-based filtering. These cut down your payload sizes so clients are only ever requesting the exact data they need. Next is caching. If a client sends an if non-match header, the server can reply with a 304 not modified, which drastically cuts bandwidth and compute costs. And finally, you absolutely must avoid chatty APIs. These are APIs that expose a huge number of tiny resources, basically forcing clients to make dozens of excessive requests just to piece together a single view. Nobody wants that.
Section 5. API security and rate limiting. Time to install the locks and alarm systems. To really protect our infrastructure from abuse, let's trace this visual security flow. So, an API gateway sits right at the front, routing all that traffic from client applications. It relies heavily on a dedicated authentication service and an authorization service before any traffic ever touches the API server or the database. This kind of layered architecture ensures that initial security checks and token management happen securely and efficiently before your core business logic is ever executed.
And to maintain that critical statelessness we highlighted earlier, we use JSON Web Tokens, or JWTs, which are often layered with OAuth 2. In this flow, the client requests a login, the server validates everything, generates a JWT, and sends it back. For every single subsequent request, the client passes that JWT right in the authorization header, so the server verifies the identity computationally without ever having to look up a session state in memory. It's secure, and honestly, it scales infinitely.
But hey, what happens when an authenticated user just goes rogue and sends way too much traffic? Well, we use rate limiting and throttling. Think of it kind of like a toll booth. Rate limiting sets a hard barrier, a strict cap on request volume within a specific time window. If you cross it, boom, you get a 429 too many requests error. Throttling, on the other hand, is a much softer approach. It manages the traffic flow by slowing down and spacing out those excess requests rather than just outright rejecting them. Both are fantastic at protecting your API from being completely overwhelmed.
Now, to actually implement these, you've got a few algorithm choices: fixed window, sliding window, token bucket, and leaky bucket. For REST API specifically, the token bucket algorithm is kind of the secret weapon. It allows for controlled bursts by accumulating tokens over time, which makes it incredibly tolerant of natural, everyday traffic spikes without randomly penalizing your clients during low activity periods.
Which brings us to Section 6, the Richardson Maturity Model. This is the path to true API enlightenment.
To actually reach that API enlightenment, we can grade our architecture across 4 distinct levels. Level 0 is what they lovingly call the chaotic swamp of POCs, plain old XML, where literally everything is just opposed to a single URI. Next, Level 1 introduces individual URIs for distinct resources. Then Level 2 adopts those standard HTTP verbs we went over. And finally, Level 3, the ultimate state of API maturity, introduces hypermedia controls. That Level 3 maturity? That is also known as HATEOS, hypertext as the engine of application state. It's quite a mouthful, I know, but this is where your API essentially acts like a finite state machine. The client doesn't actually need prior knowledge of your entire URI schema. Instead, the API response itself provides navigation hyperlinks to related resources. The client navigates dynamically, exactly like a human clicking links on a web page. It is incredibly flexible. Here's the thing though, even the most mature, beautifully designed API is going to change eventually. Business requirements always evolve. And that is exactly why you absolutely must version your API from day one. Whether you decide to use a URI version like /v1/users, a custom header, or content negotiation, versioning is a non-negotiable necessity. It's the only way you can introduce breaking changes without completely destroying the existing client integrations that are already relying on your service. So, as we wrap up this explainer, I want to leave you with a bit of a provocative challenge. Think about your current project. If your API documentation just completely disappeared today, could a new developer successfully navigate your system using only the links, the URIs, and the HTTP verbs you left behind? If the answer is no, well, it might just be time to take these global principles of RESTful design and start refactoring. Thank you so much for joining me on this explainer, and I will see you in the next one.